my name is John. I'm down with the physics department. And I'm excited to introduce Kelsey and Patricia, who helped me work on the demo set project to send payloads up in the atmosphere. They'll tell you all about it. So give a hand to them.
Hi, I'm Patricia.
And I'm Kelsey.
We're working on the demo set project. In the demo set project, it's run by the Colorado Space Grant Consortium and NASA. The goal of the project is to send a payload attached to a weather balloon up into the atmosphere and look at the difference between muon counts versus the altitude.
So it is believed that the majority of muons are caused by cosmic rays, so we are going to send the payload to test them.
In my research project, I focused on the Geiger counters, which are used to detect muons.
And in my research, I focused on Einstein's theory of special relativity, so that we can account for that when detecting muons.
Here's a picture of the frame of the payload, and it's a 3D printed modular frame. Over here is a 3D printed box which holds the detection devices, specifically 2 Geiger counters and scintillators. And these detection devices are connected to an Arduino, which is the brain of the operation.
And here is an image of the completed payload. All the equipment is in it, and here is the battery, and it also includes a barometer, which measures pressure, and from that can determine the altitude at which the payload will be at.
So now let's explain the process of the payload launch. So on the launch day, we turn on the equipment and make sure it's all operational. Then we attach the payload to the weather balloon, and it is launched, and data is then collected. At effigy, the weather balloon bursts, and the payload begins to descend.
The payload is rapidly descending downward, so a parachute opens to slow that down, and then the payload lands on the ground. The final step is the researchers have to go find where the payload actually landed.
So,
one of the main things that Kelsey and I did during research was help develop and create a new 3D printed box that will house the detection equipment.
We designed this box on SolidWorks and printed it out on a 10-6 3D printer. While designing the box, we kept in mind that it had to remain airtight, and so we came up with this sliding technique for the lid. The box has to remain airtight so that it keeps a constant air pressure, so that the Geiger counting and scintillators can work properly. Later on, we also tested to make sure that our box actually stayed airtight. So when cosmic rays enter our atmosphere, they collide with particles like carbon. A product of these collisions is muons. And muons are a source of ionizing radiation. And we can detect this ionizing radiation.
So one of the ways that we detect muons are with Geiger counters and scintillators. A scintillator contains a crystal made of sodium iodide and a photomultiplier, which is just a fancy word for light detector. When a muon passes through the crystal, light is emitted and then it is detected.
When a muon passes through a Geiger counter, a current is produced and then counted. The scintillator and Geiger counters are connected to the Arduino, which is used for a coincidence circuit.
So now that we know about muons, are detected, let me tell you more about them. So muons travel at 98% the speed of light and have a mean lifetime of 2.2 microseconds. If you did the math, muons should be able to reach our elevation. Yes, they do. If you wanted them to reach our elevation, they would have to travel approximately 46 times the speed of light. And if according to Einstein's theory of special relativity, that is not possible. So we must account for relativistic shifts. So Einstein's second postulate was that the speed of light in a vacuum is always constant, and that's the fastest you can go. Two weird things happen when you follow that. One of them being length contraction and time dilation. Length contraction is when an object or a particle is moving at speeds near the speed of light, and lengths are either expanded or contracted. This is all relative to an observer, of course. And time dilation is when movement clock on a fast object ticks slower, also relative to an observer. And you can see that in these two images here. This demonstrates time dilation, and this is length contraction. And just in case anyone doesn't know, C stands for the speed of light. So I wanted to test Einstein's theory. So we brought a photomultiplier tube up to Estes Park, and we let it run and collect data for 1 hour. This experiment was once again conducted in Greeley, Colorado, which is at a lower elevation, and then we compared the results. As you can see, the mean Muon lifetime in Estes Park was 2.4 microseconds, while the mean Muon lifetime in Greeley was 2.2 microseconds. And you can see that there were more muons detected in Estes Park versus Greeley, Colorado. And this demonstrates Einstein's theory. So in Kelsey's research, she focused on these simulators, and then I focused on the Geiger counter. So the Geiger Muon tube is the part of the Geiger counter that detects the muons. The Geiger tube does not specifically detect muons, but ionizing radiation. Muon events are the source of ionizing radiation, but these muon events aren't the only ones, and so we have to filter out other particles so that we can get just the muons. We can do this by changing their arrangement or connecting them to the coincidence factor. For my research, I wanted to increase the probability of detecting muons and subsequently lowering the uncertainty associated with the detection. I focused on the Geiger counter's orientation and geometry. Okay, so now I'll explain how a Geiger Muon tube works. A Geiger Muon tube is an electrode, meaning that it has a cathode part and an anode part. The cathode part is negatively charged, while the anode part is positively charged. The Geiger tube has a cylindrical shell, and that's the cathode. And there's a wire running through the center, which is the anode. The space between the cathode and anode is filled with noble and halogen gases. So when a muon enters the Geiger tube, it collides with the noble gases and excites it, and a UV photon is emitted. The UV photon then ionizes the halogen gas, and a cascade of electrons is created. These electrons are attracted to the anode wire, and a current is produced, and we count that current. So, since the cathode and anode are charged, there are potentials associated with them. The cathode shell is grounded, meaning the potential is zero. And the cylindrical shape of the shell causes the electric field inside the tube to cancel out. And so the anode wire creates a positive electric field. The shape of the tube gives it an equipotential surface. And so that means that the potential is the same everywhere along the surface. A sphere would be an even better equipotential surface, but since the Geiger Muon tube is an electrode, it has to be the cathode part and the anode part. And so the anode would be in the center of the shell,
and there would have to be a wire running from the anode, and that wire would compromise the symmetry of the sphere. Therefore, this cylinder is the best shape for the Geiger Muon. So after determining the cylinder is the best geometry, I decided to play around with the arrangement. In the payload project, there are two Geiger counters and a scintillator stacked on top of each other. The line here depicts the pathways that the muon can travel. From the green line to the red line is called the detection window, and in the payload, and in this one there are 2 detection windows. Originally, I planned to have 5 Geiger counters arranged in a pentagon, but the Arduino can only process 4, so I changed it to 4 Geiger counters in a square. By changing the arrangement, I was able to increase the probability that muons would be detected, and so the number of detection windows increased from 2 to 4, and the area of the detection window also increased. Here's a picture of the 4 Geiger counters put together, and I was able to attach it to an Arduino, and we programmed the code for it to the Quinton circuit, but unfortunately the code wouldn't upload to the Arduino, and I wasn't able to test my design.
So some other things that we did during research is that we tested our box for durability. First, as stated before, our box needs to be airtight in order to keep the Geiger counters and other detection equipment at a working pressure to avoid arcing. So we sealed our box with bathtub caulking. This can be seen right here. The bathtub caulking is waterproof but not airtight. So the first time, it lost pressure inside. Next, we tested it by dipping it in acrylic resin, and this held better, but because of the microscopic leaks in this resin, it still didn't hold pressure. So further testing and trial and error needs to be done to make a box truly airtight.
So we also conducted some tests on the payload itself to make sure it was structurally sound. And one of them was the whip test, and it simulated the acceleration the payload would encounter during the launch. And the whip test is you tie a rope to the payload and swing it over your head. We determined that it is sound enough for the launch.
Another test that we conducted was the impact integrity test, in which Patricia and I kicked the payload down the stairs. It was hysterical. The payload held up great, even though Patricia punted it down the stairs instead of lightly kicking it. Another thing that we did was that we had to help design a new scintillator crystal. The reason for this is that scintillator crystals don't come small and cheap enough to put inside the payload, so we decided to make our own.
We were able to create it, and we tested it by driving it up to Estes Park and had it collect data as we changed in altitude. We were just trying to see how the data changed as altitude increased. And as of Sunday, we were able to have a working system between the scintillator, Geiger counter, and Arduino.
So moving forward, we are going to launch the payload on August 21st during the solar eclipse. It is believed that the majority of cosmic rays come from extrasolar bodies, so it will be a perfect time to test this hypothesis when the sun's rays are covered by the moon. So accomplishments we made during our 60s is that we engineered a new structural housing box for our detection equipment.
We were able to make that scintillator.
We were able to demonstrate Einstein's special theory of relativity.
We studied electromagnetism and the orientation and arrangement of Geiger counters. And we studied the Arduino and programming and data of it.
Our research wouldn't have been possible without these individuals such as Dr. Matthew Pina, John Raynor, and Josh Spender in UNC's Department of Physics.
We would also like to thank Ball Aerospace and Technology Corporation, Union Pacific, and the Webb family for funding our participation. And we would like to give a very extra thank you to
Tigger and Dean
for their emotional support. Thank you.
What does it mean, Muon?
Okay, so when the carbon rate slide, like carbon, for example, they're many products, but a muon is one of them, and a muon is a negatively charged particle. And so when muons accelerate, they create ionizing radiation.
And ionizing radiation is just light that has the potential to strip an electron with something.
Great. So why did you, I guess, why was your design like a 2,000 meters square rather than, how did you come up with that? Well, okay, so the question about why I chose this pentagon original. So originally I wanted to increase the number of diagonal tubes because that would make the Winston circuit more effective and give increase the probability that there would be a muon count. And so I just changed that. And 5 makes the pentagon. And then since the Arduino can only process 4, I then changed it to a square. And I didn't want to put them in a line because I wanted to make the area as hard as possible.
Yeah. Oh, yeah. Yes. How many become just me? Actually, the program did that for us. So, what is the data? What is it? So, you can see in the histogram that on the y-axis, in Estes Park, it's just a larger y-axis. So there's more muons detected, and that's basically the easiest way that you can see that. One of the shortcomings of my project was that we weren't able to bring a multimeter up to Estes Park, so our K2 values are kind of large. That's what the reason why I asked is that when I started to use the it's kind of a, yeah, pretty small distributed, right? Yeah. So I would say that my suggestion is what we're going to do that means not the best measure than we see when we have one and normal distribution. So I think my suggestion is that you can use the median instead of the mean looking at the stuff that you have. Thank you. Okay.
So I saw that your payload was 3,000 what we had on it. So why do you use the aluminum foil?
Oh, it's not aluminum foil.
Okay.
I forgot.
Just an insulator, just a bit more.
Jay?
So I know you guys talked about aluminum foil, like what do they do and why do they do it?
Okay, so muons, they create ionizing radiation, which affects military and aviation, and by studying them, we can protect pilots and
Make air travel more safe by knowing the causes and effects of the ionizing radiation particles.
and protect equipment.
Thank you.
Then,
So there is a certain image of what is that?
Can you repeat your question? Oh, the coincidence circuit? Okay.
so when a muon passes through, the coincidence circuit will only count a muon if 2 of the 3 Geiger counters have a reading, and so it can be 2 of the 3 in general.
And so the reason that there is a coincidence circuit just in general is because there's definitely other particles in the atmosphere. So if you just went through one per se, it could be something else besides muon. We only want to collect data on muon. Does anyone else have any further questions?
So when the payload travels up into the atmosphere, at that point when the weather balloon pops, is that just due to the atmospheric pressure? Or?
Yeah, so it's full of air and then it can't withstand it for a while.
Sorry?
How often do you lose the actual payload boxes?
Well, there's a GPS tracker attached to all of them, and John said in past payload projects that they have to like drive hours and hours of what felt like an eternity to find the actual payload. So I don't think they lose it actually ever, but finding it's always a fun time.
So how high will the payload actually be on?
I'm not sure about the specifics, but I think it's around 45,000 feet.
100,000 feet, actually.
Yeah, more like that.
Yeah. Yes.
So the vacuum integrity of the box is still a work in progress?
Yeah.
Do you have a direction?
Well, we weren't able to determine where the leakage was, but I think we're going to try and expand the box and put the lid on again.
It was a very small leak the last time that we tested it. Acrylic resin tends to like crack where it's not attached anymore, and then this box can't be the box. This box was meant to be testing actually, so that's why it's broken. But there was just a very small leak along one of the sides of the lid from the sliding lid and the actual box. It was almost there.
Dylan?
So you guys talked about like Muon affecting like pilots and stuff. Like, what does it do like in air travel? Why is it unsafe?
I'm not sure about the specifics, but it's radiation. And so like, that means that it strips the electrons, and so that totally messes up the stuff. Yeah. Sorry, we didn't discuss this